So we want to do some more verifying examples here. This first one looks a little tricky. You have two functions on the left that don't look anything like the two functions on the right. But here's what I do notice structurally. I notice that whereas on the left side I have two different terms, on the right side I only have a single term. Whenever I see something like that, I think what I'd like to do is I'd like to try to get my two terms on the two-term side together to become a single term. It's hard to even see how we could do that as it is, so I'm going to use reciprocal functions to rewrite cosecant 1 over sine, cotangent as cosine over sine. And now I actually see something I kind of like. What I see is two terms that have a common denominator. So I don't even have to work to get these two terms together. I can just subtract them immediately, knowing they do have a built-in common denominator. Now this gets me to a situation in which I have a monomial over a binomial on the right side, and there it is right there. And on the left side, a binomial over monomial. And here's what's very special about these. The binomials are identical, sine and sine. The binomials are almost identical, except one of them is a difference and one of them is a sum. Those are actually called conjugates. They are the factors you get by factoring the difference of squares. And whenever you see this format, this is the general format right here. Okay, so you have on one side binomial with the sum on the other side in the opposite location. So instead of in the numerator and the denominator, the same binomial except with the opposite sign, so a difference in this case, and then your monomials are exactly the same, also just in different locations. One of them is a numerator, one of them is a denominator. Whenever you see this, you will very often, I'm not going to say 100% of the time, but probably 80% of the time, you're going to use conjugates. And the conjugate of 1 subtract cosine is 1 plus cosine. And so we're going to multiply both the top and the bottom by 1 plus cosine. Now, here's the little check you can do to make sure this is a good idea. This makes sense to do. If I multiply 1 plus cosine times 1 subtract cosine, I'm going to get 1 minus cosine squared, which is a difference of squares. Is that something that we could substitute from a Pythagorean identity? If you multiply conjugates and you can substitute something from a Pythagorean identity, then you're on the right track. If you can't, then conjugates is probably not the way to go. Is 1 minus cosine squared a substitutable expression? And it is, because we know that, sine squared plus cosine squared equals 1. And so if I subtracted cosine squared to the other side, I would get sine squared is equal to 1 subtract cosine squared. You see that? And so not only is it substitutable, but look what it's going to turn into. It's going to turn into sine squared, which is exactly what we need to get on the numerator anyway. We need a sine, not necessarily a sine squared, but a sine. Things are looking good. So in those instances, we definitely want to use conjugates. You will see this again as we work through these problems. But anyway, we're going to go ahead and do this. 1 subtract cosine squared over, I am not going to distribute here. And why would I distribute on top and not the bottom? You're just going to have to trust me on this one until the next step, and then you'll understand why this is the way we're going about this, okay? We're going to go ahead and make that substitution we were talking about now. 1 subtract cosine squared becomes sine squared. That's from the Pythagorean identity. 1 plus cosine sine, and then sine over 1 plus cosine. And here's actually two reasons why you did not want to distribute the bottom. Okay, the first reason is because look what we want to end up with on the bottom. 1 plus cosine. What did I just multiply by? 1 plus cosine. I don't want to mess that up. I just got something that I want to get. I don't want to distribute through and get sine plus cosine sine, which is something I don't want. But the other big reason is what you see right here. Sine squared, and then we have multiplication here, which means I can cancel. I want to cancel this sine with one of those sines, and that sine goes away. If I had distributed it, it would not be so simple. I would not get that to go away. We're done. We are done with this problem. All I have left on the top is sine theta. All I have left on the bottom is 1 plus cosine theta. And that is the magical power of the conjugate in a wide family of different verification problems. Conjugates can be very, very useful. All right, so done with this one. Let's go to the next one. There's a couple different ways you could attack this, but I think the best way to do this problem is to just ask yourself this question. What do I see on the left? Well, I see some secant squareds and some tangent squareds. What do I see on the right? Well, I see some secant squareds, but I don't see any tangent squared. So logically what this means is I want to get rid of these tangent squareds. I want these dudes right here to go away. Bye-bye tangent. So let's make them go away through the magic of substitution. Luckily it's tangent squared. And so what I can do is substitute from a Pythagorean identity. If it was not a squared, I would not have the easy substitution that I would look for to turn it into a secant squared. What is tangent squared equal to? Well, we know that 1 plus tangent squared is equal to secant squared. That's a Pythagorean identity. So to solve for tangent squared, I would have to subtract the 1 to the other side. So tangent squared is secant squared. Subtract 1. And the rest of this problem really just comes down to algebra. We are going to distribute. So negative 5 secant squared. A negative times a negative is a positive, so plus 5. So step 1 was algebraic distribution. Step 2 is algebraic simplification. 9 secant squared subtract 5 secant squareds is 4 secant squareds. And then finally, our last algebraic step is actually the commutative property. We have to commute our two terms because 4 secant squared plus 5 is awful close to 5 plus 4 secant squared, but it's not identical. And with an identity, we really do need to work our way all the way to an absolutely identical step. And that will pretty much do it, huh? This verification is done. Let's see, what do we have here? This one, boy, you could do this one a couple different ways. You could say, well, I only have one term on the right side. I'm going to get a common denominator with that one on the left by making it into a 1 subtract cosine over 1 subtract cosine, but that's a pretty ugly way of doing it. Here's an easier way of doing it, but you do have to have a little bit of factoring skills to do this. So let's take a look. When I look at the left side, I see some sines and some cosines. When I look at the right side, I only see cosines. So intuition should tell you I kind of want to get rid of those sines, and we can, because sine squared directly from the Pythagorean theorem is 1 subtract cosine squared. Okay, so just to make sure we're not getting lost in this substitution here, this is our identity. Sine squared is equal to 1 subtract cosine squared. That was our substitution. Okay. Where do we go from here? Well, this is where that factoring has to come in. What some people would want to do, is kind of look at this right here and say, hey, can't I cancel a cosine on top with the cosine on the bottom, and then I would just get, you know, a cosine on the top, and 1 minus 1 is 1, and then I have the negative or 0, and then I'd have the negative cosine left. Boy, that'd be nice, wouldn't it? Well, it actually wouldn't work out the way you wanted to anyway, because we'd have to distribute this negative 1 into the negative here, and we wouldn't get a negative cosine, we'd get a positive cosine. And so cosine is not equal to negative cosine. But furthermore, it's just completely algebraically illegal to ever cancel over addition and subtraction. You can only cancel in a fractional sense over multiplication. You cannot cancel when you have addition and subtraction signs between your terms. So you just can't do that. But here's where the factoring comes in. Here's what we can do. 1 subtract cosine squared is a difference of squares. 1 subtract cosine. 1 plus cosine. There's your conjugate pairs there. And it's really hard to say subtract instead of minus all the time, but I'm trying to be as technically accurate with your vocabulary as I can. So here's what we've done. We've created a multiplication situation. Now I do have multiplication. Now I can cancel this full term with the only term that's on the bottom. You can cancel over multiplication. Now there's still one area left where you might make a little mistake, and that's, you know, here's what we have right now. 1 subtract 1 plus cosine. If you're not careful with your parentheses, it's extremely easy to make this mistake. Okay, but if you're careful with your parentheses, you probably won't. Or at least you'll have a better chance of not doing it. We actually have to distribute this negative sign. It's really kind of like a negative 1 multiplying through, but we're subtracting both parts of this binomial. So I'm going to get 1 subtract 1, but I'm not going to get plus a cosine. It's actually going to become a negative cosine, which is actually a really good thing, because that's what I need. We need a negative cosine, not a positive cosine. So there you go. A little bit of substitution with Pythagorean identities, which I think you've noticed happens a lot in these problems. And then some factoring. And we're going to be reviewing factoring even more in the coming days. So this will become more and more natural for you. But you haven't really seen the factoring problems very much yet. All right, so here's one of those where you first look at this and your first instinct is, hey, maybe this is a conjugate problem, because I see the cosecant subtract 1 over the cosecant add 1. Those are conjugates. Shouldn't I use conjugates here? And your first instinct is, yeah, go for it. But remember that check. We want, when we use our conjugates, to link to something that we want on the other side. And when I do cosecant minus 1 times cosecant plus 1, I get cosecant squared subtract 1. I could turn that into a cotangent, but I don't see a cotangent on the other side. Cotangent squared is not going to help me when I have signs on the other side. So this is not the relationship that we want. I mean, when you first learn how to use conjugates, I can completely understand where that would be a good intuition, but it's not. So the question becomes then, what other relationship do we have between cosecant and sine? What other relationship? Well, the relationship is that cosecant is defined as the reciprocal function of sine. That's where it comes from. So what I'm actually going to do is I'm going to turn these cosecants into their reciprocal functions. 1 over sine, and cosecant becomes 1 over sine on the bottom also. And that's the easiest way to get what we want, which is sines. Now, we're still not looking exactly like we want to finish with, but we're getting closer, and I couldn't leave this side over here like it is anyway. This is no bueno. We have what we call complex fractions, a fraction within a fraction. We couldn't leave it in that format anyway. And the easiest way to eliminate fractions is by multiplying by a common denominator. So I'm going to be real careful with your fractions. Whenever you distribute with these problems, always try to throw fractions in. But I'm going to multiply by sine over sine. Sine on the numerator, sine on the denominator. Sine over sine is just 1, so you can always just multiply by 1. But look at the good things that happen when we do this. Sine times 1 over sine, well, that's just 1. And sine times 1, well, that's just sine. And then on the bottom, same idea. Sine times 1 over sine, 1. Sine times 1, sine. And what do you guys think? Think we're done? I think we're done. Very nice. The trick there was just to use the reciprocal functions and not get caught up in the conjugates. Here's another one that has that magical format. Look at this. We've got the binomial here and the binomial here that are almost identical, except they're opposite conjugates. And we have the monomial here, and then the opposite location in the denominator, the monomial here. Isn't this exactly what we were looking at when we looked at this formation a little while ago? Okay. Learn to recognize this formation, because anytime you see it, you're almost absolutely positively going to use conjugates. Okay, not 100%, but most of the time, probably 80-90% of the time. So let's go ahead and do that. Let's go ahead and use conjugates here and see what happens. Let's do cosecant plus 1, and then we have the cosecant subtract 1, and the fraction on the denominator we just have the cotangent. So I still need to multiply the cosecant plus 1 by the bottom too. Some people just multiply it once and then multiply the top and the bottom. That's not actually proper. If you just write cosecant plus 1 once, it's just cosecant plus 1. You have to write cosecant plus 1 over cosecant plus 1 to get the value of 1, which you are allowed to multiply by. So please be careful about that little technicality, just to make sure that your work is accurate. So here's where we are. We're going to get difference of squares. We're going to get cosecant squared, subtract 1 over. And remember, we don't want to distribute the denominator. Why? Well, maybe the most obvious reason is, what do I want to get in the denominator eventually? That, cosecant plus 1, cosecant theta plus 1. What did I just create in the denominator? Cosecant theta plus 1. We don't want to mess that up. We are not going to distribute that by cotangent. So just be patient. You have to learn to be patient with that. The other reason isn't really apparent until the next step, but when it becomes apparent, it really works nicely, whereas if you distribute, then you run into all kinds of problems, all right? So what is cosecant squared minus 1? Well, I know that 1 plus cotangent squared is equal to cosecant squared, so I think cosecant squared subtract 1 would be cotangent squared. It's nice to see the computer processing speed is no better than it was last week. So the handwriting, I know, is not ideal, but hopefully you can read it enough to help you out. So here's our cotangent on the bottom, canceling with one of the cotangents on the top. That would not have happened if we had distributed the cotangent, so it's a good thing we didn't. So I'm going to have cotangent theta on the top. I'm going to have cosecant theta plus 1 on the bottom, and holy cow, that's what we wanted. We have ourselves a verified identity. Let's all celebrate. Here's another one that looks like you might want to use conjugates, but in the long run it doesn't really help you, because if I did multiply the cosecant plus 1 by cosecant minus 1 in the numerator up here, I would get cosine squared subtract 1, which would turn into a negative sine squared. But I don't have any kinds of sines over here, so that just doesn't help. But remember, cosine is related to secant through the reciprocal identity. So let's just do our 1 over secant plus 1 over 1 over secant theta subtract 1 is equal to 1 plus secant theta over 1 minus or subtract secant theta. And once again, we don't like these complex fractions over here, so let's multiply by that common denominator, which is secant theta. We're allowed to do this because secant over secant is just 1. We're going to distribute on the top. We're going to distribute on the bottom. What are we going to end up with? Well, secant times 1 over secant is 1. Secant times 1 is secant. secant times 1 over secant is 1. Secant times 1 is secant. I wish I had some confetti because it's time to celebrate. We got that one pretty quick. 3 steps, not bad. Actually, only 2 steps, right? All right, this last one is probably the longest one you see. And this one really does, I mean, there's ways you could do this that may be a couple steps shorter. If you recognize that one plus sign and cosine theta, even though they don't look anything like as far as denominators go, if you start looking at cosine squared versus 1 subtract sine squared, they're actually closer together than you may think. But what we're going to do here is we're going to suck it up and we're going to get a common denominator. So the common denominator is going to be cosine theta times 1 plus sine theta. So I need another cosine theta over here. So I'm going to multiply by cosine over cosine. And over here I need the 1 plus sine theta. So I'll multiply by 1 plus sine theta over 1 plus sine theta. Multiply by the original fraction, which was 1 plus sine theta over cosine. Notice that anytime I have binomials, I'm always putting them in parentheses because I'm getting ready to do some possible distribution. And you can't have distribution unless you have the parentheses. Well, here's our common denominator. Cosine times 1 plus sine. What else do we have on top? Well, we've got cosine times cosine, which is cosine squared, plus, what do we have here? Oh, we're going to have to FOIL, aren't we? We're going to have to do, firsts and outers, and inners, and lasts. So if you're into the Algebra 1 acronym of FOIL, that would work for you. I'm just going to kind of do it here in my mind. 1 times 1 is 1. I'm going to get a 1 times sign and another 1 times sign. I'm going to get 2 signs. And finally, I'm going to get a sine times sine, which is sine squared. So remember, when you distribute 2 binomials, you have to kind of make sure you get all of the pieces of it. You can't just do 1 times 1 and sine times sine. Very common mistake. 1 plus sine times 1 plus sine is 1 plus sine squared. But you're not fully distributing if that's the way you are doing things. So be careful about that, please. All right, what do we got here? Well, check this little trick out. I know I've got a cosine squared over here. I'm going to use the commutative property. I'm going to slide the sine squared from the end all the way over here. Because we all remember what sine squared plus cosine squared is equal to. At least I hope we remember. I hope we remember that this dude right here is just some of you guys that are thinking ahead, maybe trying to, turn that into a 1 ahead of time and then add it to the other 1 ahead of time and get, go straight from the step right here to the step that we're about to go to, where you put the 1 and the 1 ahead of time, together ahead of time. Don't do that, because then you're not showing where the other one came from. You're not showing it was a substitution from a Pythagorean identity. Sometimes you're going to get in a hurry, especially with these longer problems. You're just going to have to hang back and be patient. You don't want to get yourself in trouble by not showing substitution steps. We are going to factor now a little algebra, pull a 2 out from the top. I'm just going to get a 1 plus sine left over in there, which is awesome because I have a 1 plus sine factor on the bottom also. And we all know what happens when we have common terms separated with multiplication and fractions. We can cancel. So all I have left here is I have a 2 divided by cosine, which I could also write as times 1 over cosine, right? And I just wrote it that way because I think you guys might see it a little bit more clearly. Hey, 1 over cosine, I know that. That's the reciprocal. function of secant. That's it. So cosine and secant are reciprocal functions, I guess is the way to say that. And voila, long, not pretty all the way, a little bit ugly, but you got her done. Okay. Good long one to end on, I believe. No, I guess there is one more left. But this one, I believe, is very, very similar. Let's go back and check. Oh yeah, look at this. 1 subtract sine squared over 1 minus cosine. And this one is just 1 subtract sine squared over 1 plus cosine. You can see they're very similar, and they actually work in almost the exact same way. I mean, I could start it off for you guys by doing a substitution of the Pythagorean identity. Sine squared is 1 subtract cosine squared. And then we factor, right? Difference of squares. You're going to see it a lot, so gotta love your factoring. You're going to see factoring of all different sorts. In fact, the next video that I make for you will be all those factoring examples to make sure you guys are good with that. Well, I guess we've almost finished this one. We might as well finish it off, huh? 1 subtract cosine, quantity 1 subtract cosine. Don't forget to distribute the negative sign. Those of you that lose your parentheses are going to have this problem continually, that you're going to lose signs, because if you don't have those parentheses, you're not going to get the double negative to get the positive cosine, and yeah, that could cause problems. Big problems. Washington, D.C. level problems, huh? So this was the homework from that follows this assignment. I think some of you guys have already taken a pretty good shot at it. If not, make sure you give it a run. And I hope this video is helpful.